Okay, YouTube, in this module of videos, we're going to be focusing on using matrices to solve systems, but those specifically that have either no solutions or infinitely many solutions are what we're going to be focusing on. So in previous videos, we've seen systems that we solved using matrices and Gaussian elimination present us with at least one solution, but not infinitely many. And we will refer to these going forward as what we call consistent systems. And that is to say that any system that basically gets an answer, at least one answer, is going to be considered to be consistent. But we're going to refer to the systems that we've seen previously where we got like one answer or just a set number of answers, but we got an answer and it wasn't infinitely many as consistent independent. And so we'll say that systems that have at least one solution but not infinitely many, these are systems that we've seen before. We call them consistent independent. The two that we're going to be focusing on really in this video are going to be the inconsistent systems, or the consistent systems that we refer to as being dependent. So the difference between these really quickly is just that if we have an inconsistent system, inconsistent basically just means no solutions. There's going to have a system where there's not a set of solutions that makes all of the equations in the system true at the same time. So we say that this is a system that has no solutions, and also it's worth noting that these are systems that result in statements that are not true. Okay, so we're going to see that happen here in this first video. Now, in the next videos, we're going to look at consistent dependent systems, and these are systems that are consistent, so it means it has an answer. It's just that when we have dependent systems and not independent, these are systems that have infinitely many solutions and are said to be dependent. And so these are systems that often result in statements that are always true statements. And again, we'll see those in the next video. But let's go ahead and start by taking a look at just a system here that I can tell you right now is inconsistent or is going to have no solutions, and kind of talk about what that looks like and how we kind of carry out our operations when we look at something like this. So the first thing we want to do is absolutely write an augmented system or an augmented matrix to go with the system. So it looks like our first row here we would have 1, 1, that'd be a negative 1 here, negative 1, negative 2, and then we'll put our bar here to make this an augmented matrix, and we have 2 as our constant. And so our next equation looks like we have 2, negative 3, and 6. So 2, negative 3, and 6, and then we have 5 over here. And then our last equation, we have 3, negative 4, positive 4, and then 12. And so what we want to do is just go ahead and work our Gaussian elimination so that we can get 1s down the main diagonal and 0s elsewhere. Now it seems to me that we already have a 1 here, which is wonderful news because we do want a 1 in the top left corner. So here's what we're going to do. We're going to use that 1 in order to get the things below it to be zeros, to get these to become zeros. And so remember that with our matrix operations, we are allowed to either scalar multiply a row, or I guess we could switch two rows, or we could scalar multiply and add it on to a row. And so what we're going to do here is this. We're going to take the first row, row 1, times a negative 2, so that when we add it to the second row, this 2 becomes a 0. And we're going to take our first row times a negative 3 and add it to our third row so that that 3 becomes a 0. So to write our operations out here, we're going to say that we're going to take our first row times negative 2. We're going to add that onto row 2. So you notice I wrote that in front of where row 2 lies. And here we're going to say negative 3 times our first row plus row 3. What that's going to do is it's not going to change row number 1. Of course, once we have a 1 in the top left corner there, row number 1 should stay the same throughout our Gaussian elimination. And then rows 2 and 3 now, they're going to start with zeros here and here because of these operations that we carried out. Now, we need to finish these off and find out the remaining operations. So let's go ahead and start with this right here. We're going to take negative 2 times all the values in our first row and add that to the values in the second row. So you can see that negative 2 times this positive 1 right here would have been negative 2, and adding that negative 2 to this positive 2 gave us a 0. But negative 2 times this negative 1 is a positive 2, and positive 2 plus this negative 3 in the second row is a negative 1. So we get negative 1. Now a negative 2 times this negative 2 up here would be a positive 4, and 4 plus 6 would be a 10. And then we'd say negative 2 times this positive 2 is negative 4, and negative 4 plus a positive 5 is a positive 1. So here's our new row 2. Let's go ahead and find our new row 3 by taking everything in row 1 times negative 3 and adding that to the values in row 3. So skipping over this first value or entry right here, we'd say if we took negative 3 times this negative 1 here, it would be a positive 3, and adding that positive 3 plus a negative 4 would be a negative 1. Now negative 3 times this negative 2 is a 6, and 6 plus this 4 would be a 10. And then we could see that negative 3 times this 2 up here would be a negative 6, and negative 6 plus this positive 12 here would just be a positive 6. And so I hope you can already see that something's up with these other two rows down here. It looks like the left side's almost identical. And so just to continue working with this here, we could say that now that we have a 1 in the top left corner and we have zeros underneath it, what we would hope to accomplish next is that we would like to get a positive 1 here. And so really quickly what I'm going to do is I'm just going to take everything in row 2 times a negative 1. So I'm going to write this on the outside. We're going to say negative 1 times everything in row 2. I'll even put a multiplication symbol there. So row 1 stays the same, 1, negative 1, negative 2, and 2. And row 3, we didn't do anything to that, so we say 0, negative 1, 10, and 6. But our second row, if we took everything times a negative 1, we would get still a 0 here, but a positive 1 here, a negative 10 here, and a negative 1 here. So now that we have a 1 here, what we're going to do is we're going to use that 1 to get rid of the negative 1 below it. And so using the techniques that we know with Gaussian elimination, what we're going to do is we're going to take that 1 times, I guess, the opposite of negative 1, which is still 1, and we're going to add it to row 3. So we're really going to take row 2, and we're going to add that to row 3 because that would get this to cancel out and become a 0. And so what I want everybody to see here is this. Let's see, row 1, 1, negative 2, and 2. Row 2 doesn't change. We have 0, 1, negative 10, and negative 1. But row 3, once we add row 2 to row 3, we get 0 plus 0 is 0. I'll go ahead and use that. We say 1 plus a negative 1 is 0. Negative 10 plus a positive 10 is a 0, and then we get a negative 1 plus a positive 6 is a 5. And so what I want to do is I just kind of want to take a time out here because remember that we started with this system being represented by this augmented matrix here. And so if we were to rewrite the system associated with this augmented matrix right here, let's go ahead and rewrite the system. I just want to show you guys what this is saying right now. It says that we have some system where we would say that this is x minus y minus 2z's is equal to 2 here in our first row. Our second row would say 0 x's plus a single y minus 10 z's would be equal to negative 1. And then our final equation would say nothing on the left side, 0 really, is equal to 5. And what I want everybody to see is that this statement right here is an always false statement. So this false statement, what this would mean is really it would imply that this system has no solutions to it. And so what we're going to do is we're going to get into this habit now of classifying systems with no solutions as just being these inconsistent systems. And inconsistent just meaning that there is no x, y, and z that when we put them into all three equations makes them all three true at the same time. And so what I'd like to look at here then on this next slide is just an instance where we're going to get another inconsistent system and talk about what is actually happening here. So I'm going to have you try this on your own, pause the video, try this on your own, and then unpause the video when you're ready to take a look at what my solution looks like here. So as we take a look at the solution here, if we were to rewrite this matrix here as an augmented matrix, we'd have 1, negative 2, negative 1, and then we'd have a negative 5 here, negative 5. And looks like our second row would be a 2, a negative 3, a negative 1, and a 0. And then our last row would be a 3, a negative 4, a negative 1, and a 1. And so let's go ahead and just talk through our steps here. Basically, we want to get a 1 in the top left corner, which we already have. And so since we already have a 1 in the top left corner, we're going to use that 1 to get rid of these entries below it. And so it looks like we'd take negative 2 times our first row, so that when we add to row 2, this positive 2 would cancel out, and negative 3 times our first row. If we add that to row 3, that would get this positive 3 to cancel out. So rewriting what we know, we have a 1, negative 2, negative 1, and a negative 5 here. I suppose we would have a 0 and a 0 here for sure. Now looking at just the second row, if we were to take negative 2 times this positive, or negative 2 here, we get a positive 4, and a positive 4 plus this entry in row 2, which is a negative 3 here, would give us a 1. If we say negative 2 times a negative 1 here, it would be a positive 2, and 2 plus this negative 1, 2 plus negative 1 is a 1. And then negative 2 times this negative 5 is a negative 10, but negative 10 plus a 0, negative 2 times a negative 5 is a positive 10, pardon me, but positive 10 plus a 0 is a 10. So now looking at our row 3 entries here, negative 3 times this top negative 2 would be a positive 6, but adding that positive 6 to the third row entry in negative 4, 6 plus a negative 4 is a 2. Negative 3 times a negative 1 is a 3, and 3 plus a negative 1 is a 2. And then negative 3 times a negative 5 here would be a positive 15, and positive 15 plus this 1 here would be a 16. So looking at what we have now, basically we could say we have a 1 in the top left and zeros underneath. Now let's get a 1 here, okay, and then get zeros underneath it. Well, now we already have a 1 there. So the neat thing about it is we're going to use that 1 to cancel out the positive 2 underneath it. And remember that what we'd do is we would just multiply it by the opposite of this positive 2 and then add it to that row. And so in other words, we're going to take negative 2, row 2, to use that 1 right there. We're going to add that to row 3, which should cancel out this 2 underneath it. So we get 1, negative 2, negative 1, and negative 5. Row 2 is now the same, always going to be the same now, 0, 1, 1, and 10. It's just that our third row, when we take negative 2 times our second row and add it to the third row, we get negative 2 times 0, which is 0 plus 0 is 0. Negative 2 times a positive 1 is negative 2, and negative 2 plus a positive 2 is 0. Negative 2 times a positive 1 here is negative 2, and negative 2 plus a positive 2 is 0. And negative 2 times a 10 is negative 20, but negative 20 plus the 16 here would be a negative 4. And so again, what you could see is that the system, if we rewrite the system associated with this right here, basically it's this bottom equation that would infer that it's inconsistent, because what we have is x minus 2y minus a z equal to a negative 5 in our first equation here. We would have a positive y plus a positive z is equal to a positive 10 in our second equation. And our last equation would simply say 0 is equal to negative 4. And so this would be an untruth. And so we could say that this is an inconsistent system. But inconsistent is basically the equivalent to saying that it has no solution to all three equations at once. And so one thing I want to talk about before we tune into the next video and look at systems that have infinitely many solutions is this idea of graphically what it is that we're talking about. And so one thing that we don't do, but we are actually talking about, is graphing these equations right here. So we graph in 2 dimensions quite a bit of the time with x's and y's, but when you extend it to x, y, and z, what you're seeing is that you have your x and your y axes, okay, essentially x and y. But what we're doing is we're saying that there's this third axis, z, that runs perpendicular to the other two, or we could say orthogonal to the other two. And this is a 3-dimensional plane about which we can graph. We could say, there's some point here that, is elevated up so far, and we say it's located in 3 space. But essentially what we've got are, 3 planes. We could say maybe if I were to graph their intercepts, we've got a plane that runs through these right here, but basically extends in all directions here. We could say that this flat 2-dimensional surface is really the graph of, one of these equations right here in 3 variables. So we have basically, you can imagine a piece of paper that goes on in every direction here is the graph of one of these equations, a plane. And what we're looking for is, we're looking for a common point of intersection, or a point x, y, z that would be on all 3 planes at the same time, okay? At the same time. So you can imagine, if we had a plane here, and then maybe another plane here, and I'm just kind of crudely sketching this in, right? Maybe right there. And then we had a third plane that cut through here. Maybe they all 3 share this common point. And we'd say this point would be x, y, z, and that would be at least a consistent system. Well, what we're looking at here is a situation where if we were to graph all 3 of these planes, then there is not precisely one point that they all have in common, or some common point of intersection between all 3. So either they're all parallel, or 2 of them are parallel and one of them cuts across it like a transverse cut here. Or, we would say that all 3 of these here just never share a common point of intersection. Maybe the yellow and blue plane here share all of these points of intersection along this line, but never this green plane here cuts across any of these. And, likewise with any of these points over here between the green and the yellow, the blue doesn't cut across it. And then the green and the blue down here, but the yellow doesn't cut across it. Basically, we're looking at a situation where if you were to graph these graphically, they share no common point of intersection. And so we would say that the system is inconsistent or has no solution, and we can always recognize these by looking for a situation where we end up with our final constraint here, or final equation giving us an untrue statement typically. Cheers.